Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, dear students. Welcome once again to the TV learning session programs. Teacher Patrick, as usual, will be with the Senior 5 Chemistry class. And we are continuing with Unit 7, which is carboxylic acids and acid halides. But this is our lesson number 3, which is about the preparation. We're just going to look at the preparation methods of the carboxylic acids. So by the end of this lesson, I would like at least to be able to mention 2, 3, 4 methods that can be used to prepare these carboxylic acids. So one simple example, before we just continue with the preparation methods, I just want to give you one question of actually what we talked about in the previous lesson, which is we're talking about the physical properties and the acidity of these carboxylic acids. That's what we mentioned, discussed in the previous lesson. So if we have these two compounds, you have so there are two compounds. Can you give the names of these compounds? So if you give the names, you remember I said when we're naming 2, 3, so you see the chlorine is attached on carbon number 3. And it is attached on carbon number 3 of propanoic acid because it has 3 carbon atoms. So this becomes 3 chloropropanoic acid. Chloropropanoic acid. And this becomes 3 fluoropropanoic acid. Remember to add the word acid as well. And this one is simply propanoic acid. Propanoic acid. So can you arrange these acids after naming them? Arrange these acids in order of increasing acidity. Can you arrange the acids in order of increasing acidity? So you'll start with the least. Start with the least acidic. Start with the least acidic. So that means you start with the compound which is a lesser acid among these ones. Few seconds as you write them down, and then we continue. Right, so you'll have the order is this. When you are starting with the least acidic, so we'll start with the CH3, CH2, COOH. That means this one is less. So that is the sign that we are going to use. Less than CH2, CH2OH, which is less than CH2, CH2, COH. So we are starting with the least and end with the most acidic. Can you explain the order? Why have you chosen explain the order? So you need to explain the order using the terms that we mentioned. We mentioned some very important terms. We mentioned about the negative and positive inductive effect. So in your explanation, you must include these words. How are you going to include the words? So you're going to say, this compound here is the least because it has a positive inductive effect, and therefore it increases the strength between oxygen and hydrogen. It strengthens the bond between oxygen and hydrogen, so the release of hydrogen ions here will be reduced. When you look at the chlorine and fluorine, these two has both negative inductive effect. But fluorine has more negative inductive effect, that is the ability to attract the electrons towards itself. That is negative inductive effect. So fluorine is more electronegative, so that effect is higher than in chlorine. So that is why this one with both electronegative but fluorine, so we have said here use negative inductive effect, but fluorine with the higher negative inductive effect caused by high electronegative value will pull the electrons, and that will make this bond more weaker, and therefore it will be released. I hope you are able to do the homework that I left behind, because that is one of the compounds, that one of the substances that we are asked to answer. Giving the reason, arranging, and then giving the reason of the arrangement. So let us continue and look at the preparation of these carboxylic acids. So the carboxylic acids, the first important method is the preparation from alcohols and aldehydes through oxidation by strong oxidizing agents. So the strong oxidizing agents, they are either potassium permanganate or potassium dichromate. So we use either these strong oxidizing agents. Strong oxidizing agents. If it is an alcohol, it will be oxidized to a carboxylic acid. If it is, so these strong oxidizing agents usually have to react in the presence of hydrogen. Concentrated sulfuric acid is a better acid to use to oxidize this because of the hydrochloric acid is not usually used because it can also be oxidized to chlorine. Nitric acid is itself a strong oxidizing agent. So that is why usually concentrated sulfuric acid is preferred during these oxidizing reactions. So as I said, as you can see on the screen over there, if you have an alcohol, CH2OH, in presence of either manganate ions and acid, you'll get an aldehyde, and this one can be further be oxidized to a carboxylic acid. The same reagents, you are using either manganese 4 or you are using potassium dichromate, the dichromate ions. So you can still be CH2 OH, the same, the dichromate ions. Dichromate ions in presence of an acid, you will get an aldehyde, which will be further oxidized. This will be further oxidized to a carboxylic acid as well. So they have to be, so it depends on the alcohol that you are, rather depending on the alcohol that you will be oxidizing, will give you the type of the carboxylic acid. For example, if you want to get propanoic acid as an example, if you want to prepare propanoic acid, so you'll need propanol, you need to oxidize propanol in order to get that. You remember, when we were talking about the alcohol, I mentioned this, that different ways can be used to to tell that the oxidation has taken place. You remember I said the oxidation is taking place on this carbon atom over here. This is the carbon atom that is being oxidized. And usually oxidation is increase in the number of the oxidation number or the loss of electrons. So there is an increase in the oxidation number here. So how do we know the increase in the oxidation number? Look at this carbon. So we can say this is X. We need to know the oxidation state of this so that it can help us to know the oxidation state of this and see whether there is an increase in the oxidation number that will help us to know that really oxidation is taking place. So this, if we call it X, this will be plus, the hydrogens here are 3, minus 2, this will be equal to 0. So X is equal to, this is plus 1 is equal to 0, so X is equal to negative 1. So it means that this is negative 1 over here, negative 1. When we come to this one, we need to know the oxidation state over there. So we also call it X, there is hydrogen, so plus 1 minus 2. So this is minus 2 for oxygen. So 1 minus is X minus 1 is equal to 0. So X is equal to positive 1, positive 1, negative 1, positive 1. So there is an increase in the oxidation state, oxidation number. When you continue to this, what happens over there? So you have X minus 2 times 2 plus 1. So that is X minus 4 plus 1 is equal to 0. Where am I getting this? There are 2. Each of them is negative 2. So that's why I'm multiplying by 2 for 1 of hydrogen. So this is X minus 3 is equal to 0. So X is equal to positive 3. So this is positive 3. That is an increase in the oxidation number. There is always an increase in the oxidation number. And I said the carboxylic acid that is needed will depend on the alcohol, will depend on the alcohol that you start with. If you want butanoic acid, then you have to start with the butanol. If you want propanoic acid, then you need to start with propanol. So that is how these carboxylic acids are prepared. That is the first method. Second method, hydrolysis of nitriles and amides with acid or alkali. So this is the hydrolysis. This is a nitrile. This is ethane nitrile. So in presence of water and acid, then you get a carboxylic acid. Carboxylic acid, nitriles and hydrolyzed in acidic or basic medium will produce the carboxylic acids. This reaction doesn't go, the hydrolysis doesn't go through straight to the carboxylic acid. So it goes through the amide, so the nitriles are reduced to the amide, and then again reduced, or hydrolyzed, beg your pardon, hydrolyzed again to the carboxylic acids, from nitriles to the amides, and then to the carboxylic acids. How does it take place? Let us go through this together. So, in this reaction, just have a look at this. This is the nitrile, propanitrile. So what happens is it has the lone pairs over there. So it means that it uses the lone pairs, because you remember we said the hydrolysis takes place in presence of an acid. So this is a hydroxonium ion. So that means it uses the lone pairs. It uses the lone pairs to abstract one hydrogen from the hydroxonium ion. And when it removes that hydrogen, this is what happens. The electron is in the double bond, breaks down to neutralize, because this one will become a positive charge, and therefore one double bond is used. So that hydrogen has been formed. This is removed from over here. So going to the next stage, the water molecule again attacks that carbonium, that carbocation, because it had formed a carbonium ion. So it forms this carbonium now. The water molecule attacks it, then it forms a compound like this. So the next one is now we can call it the proton shift. After attracting the water here, then this hydrogen rearranges. The water forms a positive charge, you remember? And therefore, if it forms a positive charge, what will happen? It means that the hydrogen will break away and goes to be attracted by the lone pairs over here. This is what happens here. Hydrogen, then we have the positive charge. Why positive charge? Because the lone pairs here have been used. When an atom uses its lone pairs, then it forms a positive charge. Then just go to this one. This is rearrangement. You had a positive charge. That means one of the bonds here, one bond will break to neutralize the positive charge, and therefore the hydrogen here, one of the oxygen-hydrogen bond rearranges itself to form a double bond over there. Because when the bond breaks, it means, what does it mean? Let me just show it over here. So you have CH3, CH2, C, double bond. Then you have N, NH with the hydrogen. This is the positive charge. And then you have this one as OH. So what I'm saying here is this. This bond breaks to neutralize this positive charge. So when it neutralizes the positive charge, what happens? It means that this one becomes positive also. So the bond here on the hydrogen will rearrange to form. So hydrogen will be released also from the solution. So in the next step, you will have this. Hydrogen has been released. This is the hydrogen which is coming from here. So when it releases, now the molecule that is formed, it again uses the lone pairs. This breaks, then it attracts the oxygen, or rather the hydrogen, that is the same hydrogen over there, and then forms this molecule. So this is the same water molecules, because there are so many water molecules which will be formed. and then forms this compound. Here it forms like that. And then let us continue. So when you look at this bond will have to break to neutralize the positive charge, so you remain with OH molecules. OH molecules. So this attracts the proton. This uses the lone pairs to attract the proton and forms this. This will be ammonia. So the bond breaks over there, and when it breaks, then there will be a rearrangement over there. Then you will have the ammonia being released. The ammonia is being released over there, and then that will be a carboxylic acid that will be formed with ammonia being released. So that is hydrolysis of nitriles to amines, to amides, and then carboxylic acids. From dicarboxylic acids, when these dicarboxylic acids are those that contain two functional groups. So like one example is this one, ethane dioic acid, which is commonly known as oxalic acid. When it is heated, it gives methanol and then carbon dioxide. When you have, this is propan 1 and 2 dioic acid, it will form ethanoic acid and then carbon dioxide gas. So this is another method that is commonly used is from organomagnesium compounds, or we call them Grignard reagents. That is the common name, Grignard reagents. When they react with carbon dioxide, they will produce carboxylic acids. And this is a simple mechanism on how they react. This is one of the examples of the Grignard reagent. So the bond here breaks, this becomes carbon, so this one will attack. And then this becomes magnesium. This is oxygen negative. There is oxygen, the negative, with carbon atom. So this reaction is very important because it increases the chain. It increases the chain of the carbon atoms. Because the first molecule that we started with over here now forms, you see it has 2 carbon atoms. That means if you have a compound, if you want to increase the chain, you have to use, if I have this one CH2 and then magnesium bromide and I add carbon dioxide, for example. So the compound that I'm expecting to get is supposed to have now 3 carbon atoms. So that means I will get CH3CH2, that is oxygen, magnesium, bromide, and in presence of the acid, it will eventually form CH2. No, this will become CH2. Oxygen, magnesium, so it will be like this. This is positive, this is negative, so you'll expect to get CH3, CH2, COH plus magnesium, like that. So this is more carbon atom. You started with 2 carbon atoms, but you end up with 3 carbon atoms. So it increases the chain. That is the most important even part of that reaction. From alkenes, carboxylic acids also can produce, alkenes, when they are oxidized, with the same oxidizing agents, they produce carboxylic acids. Aldehydes, which will be further oxidized to carboxylic acids. But the type of alkene and the carboxylic acid that is going to be formed also matters. Look at these 2 examples. If you have ethene, and then if you have propene, if you have propene, in the presence of strong oxidizing agents, potassium permanganate. So there are two different compounds. This one will change into, of course, it will first form the alcohols, which will oxidize to carboxylic acids. So this one will form methanol, 2 molecules of methanol that will oxidize to methanoic acid, HCOH. This one will produce ethanol plus the carbon dioxide. So this ethanol changes into ethanoic acid. So symmetrical and non-symmetrical alkenes. This is an example. This is a symmetrical alkene. So it will produce 2 carboxylic acids if it is symmetrical. If it is unsymmetrical, then it will have to produce 1 carboxylic acid. 2 molecules and 1 molecule over there. So I just want us to go through this homework as we come to the end of our lesson. Number 1, carboxylic acids are commonly made from primary alcohols. The alcohol is heated under reflux with excess of sodium or potassium dichromate 6 solution acidified with sulfuric acid. When the reaction is complete, the carboxylic acid can be distilled off. A, describe what you would see during the reaction. What are you expected to see? B, explain the reason for heating the alcohol under reflux with an excess of the oxidizing agent. I had talked about this even when I was talking about the alcohol, remember? C, write a simple equation using oxygen for the oxidizing agent for the oxidation of propan-1 or propanoic acid. The electron half equation for the dichromate ion acting as an oxidizing agent in presence of an acid is, so it continues, work out the electron half equation for the conversion of propan-1 or to propanoic acid. Combine that with the electron half equation given above to work out the ionic equation for the overall. So if you know the electron here have been showing the increase, so you'll know the number of electrons lost. That will help you to write the equation. Although it would be less commonly done, you could also use the same oxidizing mixture to oxidize aldehydes, propanol to propanoic. Work out ionic equation for this reaction in the same way. Thank you so much for this lesson. I hope to see you in the next. Bye-bye.